Okay, good evening, everyone. I hope you're doing great. I have already gone through some concepts. I quickly review them. I said, please, at your convenience, download the ebook that Mazia was kind enough to provide for us. That's the first thing. The other thing is, I told the whole class that I'm going to provide one package for you, a review package, all in one would be the name of it. And it contains everything like folder number 1, 2, and 3. So it can ease the job for you to quickly review the content for the midterm. The latest would be Sunday evening to receive that package on your course content. It's going to be the last folder on your course content. Apart from it, I started explaining what is happening in exception handling. Guys, if you can see the screen of the Colab, and if you can hear my voice clearly, please type 2. Excellent. If anything happens that you do not expect as the part of your flow of the program, you call it exception. Exceptions happen because of different reasons, like you want to open a file and you can't. You want to access the network, and there is no authentication that permits you to get in, and so on and so forth. For any of these reasons, if you want to check them with old-fashioned style, like if then else's, you could consider some of the possibilities, but not all of them. So exception handlings are there to help us for all the possibilities, whether you can consider them or out of our consideration lists. So the very first example that we went through was, if we want to get a number, if we just simply say 10, it's going to accept it. But if we say something like 10.22, and it is not an integer, and we cannot convert it to an integer, then it's going to raise an error, the way that you see it here, right? Or even if you say 10, TN, so it's not a number 10, the same. The errors are not that much user-friendly. You see that if you want to do the typecasting for the data, which is not, which doesn't have the capacity to be converted to integer or to float, it's going to raise error. Instead of any of these theory, let's just do some practices together. Before getting there, look at the error type that we receive here. It says that value error. So if I want to enter something and it is absolutely fine with the regulations like integer, and I want to typecast it to integer, that's going to work pretty fine. But what if I want to typecast something which is float, and I want to bring it to something like string, which is not acceptable here? Then it's going to say what? Hey, you entered an invalid integer. Absolutely right. How about the next one? If I say 10, guys, look at the changes that happened here. In here, I said the part of the code which has the possibility of facing error or exception, let's put them in the try part, and then say in the except value error, generate this string for me. Does it make sense? So we have the concept of try except or try catch in all modern languages. For instance, in C# we have try catch. In Python we use try except, and we have different form of it. Please consider, and that is one of the quiz questions that you can open it from 7:30 tonight. We always need to consider the smallest area that the error could happen. Then we are going to just make a little bit general and a little bit general. And the last one is going to be the widest possible, which is going to be general exception. Like what? If I want to open a file, the first thing that could happen is it going to be accessible or not? So file open, but a little bit higher could be the operating system, but a little bit higher could be the network problem. And generally, maybe there are something that I haven't considered, like I want to open a file to write something in it, but somebody else has done the same thing and still working with the file. So that's the general exception that I didn't consider in the list that I have, but it's beyond those kind of things, and I could catch it by saying general exception. If you can consider everything so far and everything makes sense, please type fine. Thank you very much. Let's go to the next part. So here we consider two possibilities. Both of them we just said in general exception, but let's go to the example that we have in the slides, in the original slides. It says that, okay, how can we manage asking the user to enter a correct value several times until they do so? Means, imagine that we ask the user, hey, please enter an integer, and that person insists to enter something irrelevant like strings or floating numbers, you name it. Is it possible to just get that person to a loop that enters all the possibilities except the one, and one that we expect? And when the correct value is entered, then we say, okay, you're done. Let's go outside that loop. Look at that structure. We say that while true, it's a kind of a function that we define. While true, say enter a float number, enter price, and that's what we expect to enter this float number. If a person does it correctly, then we just return the price, which should be a float number. Else, in the value error, you remember value error? In the case that the person enters something which is not float, like a string or anything, then say invalid decimal number. And then guys, because it is while true, it gets back to the while again. So enter a number, not correct, enter a number, not correct, enter a number till the time that it happens. The same applies for get quantity. And let's just run them. And in the main method, we say, okay, get a price and place it inside price. Imagine that I enter 10. It's going to say, hey, invalid number. Again, if I say 10, what is it? The price, 0.22, it accepted. Now the quantity, if I say 2.33, it's going to say, hey, invalid. If I say 2, it's going to say invalid. But if I say 2, finally, it's going to accept it. So the price, the quantity, and the total would be calculated like what you see here. Again, this is the hierarchy of exception. We always start with the most specific area, and we go outer and outer and outer. This is something that we saw in a few seconds ago. So we start with the most specific, and then we go a little bit less specific, all the way to the most general condition that could happen. After that, we want to see, for instance, everybody, please, if you open the file folder kind of browser that you see in here, if you please open that. And definitely, you have downloaded these files. If not, I'm going to drag and drop all these files for you, making sure that you can download and then drag and drop them. We are going to use these files, drag and drop them into the folder area. Ignore the warning. And then when you see something like this, please type 1. Again, if you could download and drag and drop it into your file folder and you're done with that, please type 1. Thank you, Solon. Okay, here we say enter a file name and you get it. Imagine that the movies list has nothing. And then I'm gonna say try to open a file, right? With open file, we say that for every single line in the file that we have, get that line and replace \n means the end of the line with nothing, and then append it to movies, right? When we are done with that, we can simply see what we have in the movies. For the first part, I'm going to use Control-A, Control-C, exactly the same thing to make sure that I do not make any typo, mistake or something. So movie.txt, and it doesn't raise any error. And if I say show me the movies that we have, so it's going to show you all the movies that I provided in that file. So there are 3 movies over there, right? Okay, what if I enter the name incorrectly? Like imagine that I just say movie.tx instead of txt. And what's going to happen? So it says that, hey, the file that you wanted could not find the file named movie.tx. Okay, so try that. I'm going to give you a few seconds. After you're done with that, let's see. Here it says that's a kind of old-fashioned form. I'm going to run it in front of you, but it's not the case in many modern practices, recent practices. So instead of saying sys.exit, you are going to say just exit. It's more preferable in recent form of developing, but it doesn't matter if you use it in some of the compilers, some of the interpreters, sorry, they work the same way. Exit is preferable because you don't need to import any library, and it's part of the Python, not a sys part of the Python. And the problem of sys.exit is in Colab, it shows some unwanted error messages. Here we say, hey, if exception that happens is file not found, get an object, guys. E is an alias for this, and we have an error message. So technically we print file not found error. Let me just, for the sake of these tests, say Reza, and it shows that it's not part of the original message. And then we are gonna show the error message. The thing is, E is an object that if you just send it to print method, it's gonna show you the error, the standard error message for file not found error. Let's just go through it. If everything works fine, like movie, it doesn't matter, it works like that. But if I just forget to add the last T, look, it says that error not found, right? And that's Reza. And this is the standard error that we expect. And look at this one. It says that your session crashed for an unknown reason, and that is because of the exit. Exit is there, especially if you write program in some environments like whatchamacallit, like PyCharm or Visual Studio Code, and you want to exit from the environment, then you use exit. Exit is a kind of getting outside the flow of the program, kind of exceptional exit, not a normal termination of the program. Does that make sense? And let me just go to the similar thing, just using this time, I'm sorry. This time, let's just use, if I say movie.txt, no problem. But what if I make a mistake like this? And you can see, apart from the error that we have normally here, like that thing, it says that during the handling of the above exception, another exception occurred, and that is because of using import sys. So not very much recommended. You're gonna see some unnecessary details and unpleasant error message for the non-developer users. Okay. Sometimes, for the sake of just seeing what if the operating system raise error, sometimes just for testing your application, sometimes you want to raise a specific error if the system cannot catch it directly or cannot catch it the way that you expect to be caught. You're gonna raise error. This is something that I'm not sure if you are familiar with C#. We say through new exception, right? It's exactly like that. You raise an error, and you can be very specific. You can be, you can just say raise general error. Guys, if what I covered till this moment is kind of clear, and you could relate to that until this moment, please type 5. Okay. Thank you very much. Let's go to the example that we have. You can see here we raise an exception and logging. I provided some examples for all of them. So if I say try and I want to open a file, that's the file, and the new line would be nothing. So I'm going to read every single file, every single line, sorry, and add them to the movie list that I have there. I append them there. Let's see what's going to happen. And I very much like the slides for this one. They say, guys, when an exception happens, let's consider alias E for that. It's going to tell you what is the type of exception. The good thing is, after that, you can decide to make this more complete, and then you can just be specific about the type of exception that happens. But anyway, let's just go through this. And I say, let's import csv, and then let's read mov.csv. And because we could find that, we read it, and the movies that we return contains all these movies. Okay. What if this time I forget to put v at the end of the file? Then look at here. The type of the error is nothing but file not found error, and that is the error message that it generates for us. Huh? Okay, so now I fix it, and then you can see that we can have the proper list. And this time I say, what if the file name, I forget to put the file name. What if the length of the file name is equal to 0? In that case, I raise error and I say value error. I could raise different errors and say the file name is required, the file name argument is required, and the error message is defined by me. So I just want to say this is something that we generated, right? So I run that get movies, and let's say get movies, movie.txt. You might say that, hey, Reza, you said the CSV file.reader, but why you passed txt. I just wanted to tell you that yes, the CSV reader is capable of reading normal txt files too. What if I forget to have t at the end of movie.txt? Look at this one. Look at this one. It says file not found. Guys, do you see this? And it says that no such file or directory movie is generated. This is a normal error that I didn't consider in this, but I didn't consider during here. If you want to make it flawless, whatever you have between with and return should be part of the try except kind of block. You can put them like this. I leave it to you, but look at the next possible problem, and that is when you forget to pass the name of the file. This time, it is going to generate value error. And you remember that I said the error message is defined by Reza to make sure that it is going to listen to the error that we raised here, right? That's pretty much it. The other thing that I want to tell you is what if you want to have a kind of log. It's a very simple version of logging, but you can, if you want, you can define something like log exception, and then you open a file and put the exceptions that happened inside that file for later reference. And see, for instance, you want to run an overnight process, and you see something is happening, and you want to make sure that in the morning when you get to the server, you can find what happened, what exception happened. So I say log exception and getting the error, and simply we are gonna just print those things. Let's just see what's gonna happen. I'm gonna say try to read the file, and if any exception happens, first we call the log, right? So if everything works fine, no problem, then no error message. But what if something happens like that? Look at this one. This is going to show first from log exception function. Guys, this is something that we created, and I said \n. And here we have an exception occurred, and then that is the email mechanism. Maybe you think that it is a kind of hard to follow. So I'm going to just comment that line, and I run it again. So in that case, I don't raise the error the way that you see here. So simply, if I run, it's gonna be the customized version, just the first two lines that shows the error message, customized error messages. And I mentioned some of the movies here, like Rome Open City and Citizen Kane Bicycle Thieves and so on. So I just provided some of the shots from those movies, just if you're curious to see. By saying that, we are done with this part, and we are ready to go to the next part, which is the recursion. If you're ready for that, please type 1. Thank you very much. Okay, so please just let me know in your data structure, have you worked with recursions and recursive functions? If yes, please type 2. Okay, so you have some ideas about what is happening when we talk about the recursions. So that is our job, and I quickly go through them. So first thing first, this is a kind of iterative form of functions. And if let's say def display message, and I say while true, print press Ctrl+C, and to stop. See what's going to happen if you run that. You can expect, and guys, I'm not going to try it. If you want, I can. But if I define that function, and if I just run that, it's a kind of iterative because of while true, and it's going to show you lots of press Control C to stop. But another way of handling that is going to be saying, hey, display message, and inside that you say print press Control C to stop, and then you call the function again. You call its own name again, right? It reminds me always like two mirrors in front of each other, and it reflects it to the infinity, right? So it calls it again, and that one is going to call itself again, and that one is going to call itself again till the end. So this is kind of the concept of recursive function, but I found something super useful, and I want us to watch that 8-minute video together. Just please confirm after a few seconds if you can hear and see it perfectly fine by typing 3. So I'm gonna just start playing it. If you can hear it and see and watch it clearly, please type 3.
Hi, I'm Joe James, and in this video, I'm going to explain what recursion is and how it works, and then I'm going to show you how to code a simple problem in Python using recursion. So let's start by showing an example. Find 5 factorial. Don't worry if you don't know what factorial is, I'm going to explain it right now. So it's written as 5 exclamation point, that's factorial. And what factorial is it's that number 5 times every number smaller than it. So 5 times 4 times 3 times 2 times 1. You just multiply all those numbers together. And as you multiply it all out, you get 120. So some notes here, 0 factorial is equal to 1. This is by definition. And 1 factorial is equal to 1. This is part of the definition of factorial. So with that in mind, let's find an algorithm to find the factorial for any number in factorial. So an iterative algorithm, iterative just means looping, okay? It just means looping, where you're going to use a loop. The computer goes through the loop and it calculates as it goes. So this is a simple looping function. This isn't code, this is just an algorithm. Function, get factorial for number 5, right? We're going to pass in an integer 5. We'll first set factorial equal to 1. This is going to be our running total. For x equals 1 to 5, so that's a loop that runs from 1 to 5, or 1 to this number. And then we say factorial equals factorial times x. So in other words, we're going to multiply the numbers 1 through 5 times our running total factorial. And our running total starts at 1, and then we'll multiply it by 2, and then we'll multiply it by 3. We'll multiply it by 4, we'll multiply it by 5, and then we'll exit this loop. Factorial will equal 120 when we exit the loop. So that's an iterative algorithm that uses a simple for loop. Another way to do it is using recursion. So a recursion function breaks the problem down into smaller problems. And then it calls itself, it calls its own function, it calls the same function from the function at its end to solve each of those smaller problems. And it also includes a base case or a terminal case and a recursive case. So in other words, depending on what value is passed in, it may return an answer or it may call itself again. So let's look at the 5 factorial case here. 5 factorial is 5 times 4 times 3 times 2 times 1. And what we can see when we analyze that is, gee, 4 times 3 times 2 times 1 is actually equal to 4 factorial. So 5 factorial is equal to 5 times 4 factorial. So now when we break down 4 factorial, we could say, well, 4 factorial is equal to 4 times 3 times 2 times 1. But look, we could say this, 3 times 2 times 1 is equal to 3 factorial. So 4 factorial is equal to 4 times 3 factorial. And we can continue doing that until we get all the way down to one of our base cases. And then when we get down to 1 factorial, we say, well, 1 factorial is 1. So we return 1, and then we multiply that all out. Factorial really lends itself very nicely to using a recursive solution to solve the problem, because it's really easy to break the problem down into smaller pieces by peeling off the highest number and passing in the next number to call the function again. So our recursive algorithm looks like this. We call get factorial on 5. The answer is 5 times get factorial of 4. We need to get the factorial of 4. So we call get factorial on 4. We pass in 4 as the argument. Well, get factorial of 4 is equal to 4 times get factorial of 3. So each time it's breaking the problem down one more step. And when we get down to the bottom, we say get factorial of 1. Well, we know what that is. That's 1. So we can return a 1 at this point. And then we work our way back up. We say, well, get factorial of 1 is equal to 1. And then at this point, we can say, well, 1 times 2 is equal to 2. So we pass that up. And then we say 3 times 2 is equal to 6. So we pass that 6 up, and we pass these up. And then when we get back up to 5 times factorial of 4, we get to 120, which is our final answer. And then we can return the 120 to wherever the original function call came from. So in other words, we're digging ourselves deeper into a hole, and then we dig ourselves back out of it by computing our way out of it step by step. So we have all these open function calls as we get down into this. And then we close out the function calls when we get to our base case. So the recursive algorithm works like this. Function get factorial of n. If n is less than 2, in other words, if it's 0 or 1, return 1. Otherwise, we're going to return n times get factorial of n minus 1. So this would be like 5 times get factorial of 4, right? That's it. That's how simple the get factorial recursive algorithm is. It's very, very simple. It's 2 lines of code. So recursion pros and cons. Typically, no calculations are done in a recursive solution until you reach that base case. And until then, you're opening up a whole bunch of recursive function calls, which can take up the memory. So if you have millions of pieces of data in your data set, you're opening a lot of function calls, and you could run out of memory that. So that's one of the cons. So it does not really scale up like iteration does. It requires more memory. So in some very large problems, recursion may not be a good solution. And in many languages, iterative solutions are way faster for loops. So some languages are just optimized for running for loops really fast, and they do that really well. But opening function calls, they do very slowly. And then another con is sometimes recursion is a little more abstract. It's harder to understand in iterative solutions in some cases. So wrapping your head around the solution sometimes can be harder in recursive solution. But a pro is that in some cases, it's extremely fast and easy to code. And it's extremely practical for tree traversals and binary search is where you find the leading applications for recursion, where it just makes a lot of sense. It's just the best way to do it. So let's take a look at Python code. I wrote 2 separate functions here. Get recursive factorial using the recursive method, and get iterative factorial using the iterative or looping method. So first, let's take a look at the get recursive factorial. It's going to accept an integer n. First, I do a quick error check. If n is less than 0, I'll return -1, just to indicate that there's an error. And I can't find factorials for integers less than 0. Otherwise, this will test for our base case. If n is less than 2, in other words, it's 0 or 1, we return 1, because the factorial for both 0 and 1 is 1. And otherwise, it's a recursive case, so we're going to return n times the get factorial for n minus 1. Or in the case of 6, we would say 6 times get recursive factorial of 5. And the get iterative factorial also accepts an integer n. It does the same error check for values less than 0. And then we set our running factorial counter to 1 to initialize it. We start our loop for I in range 1 to n plus 1, which actually just comes to n since it's non-inclusive. And then we multiply fact by I each time through the loop, and then we return fact.
We have two print statements. We do have one print statement to get the recursive factorial of 6 and one to get the iterative factorial of 6. So let's run that and see how it runs. So with the command prompt, we'll type Python factorial.py is the name of our program. We run that and we get 720 back for both of the two methods. They return the same value. So that's as we expected.
So
Okay, guys, if you could relate to what the gentleman said and you understood the concept, please type 1. Thank you. The thing is, in the recursive functions, we have two parts. One, the recursive case, and the other one is base case. So the base case is the part that helps us to get outside the infinite loop, right? In infinite calling itself. It doesn't have a loop the way that we expect, like while or something, but it has a kind of indirect form of calling itself in a kind of infinite loop. So the base case helps us to get outside that calling itself over and over. So we went through these two parts. Now, I want you to think about this. We say add numbers together. It's a sort of iterative form. We say, hey, for number in the range of the upper, for instance, I pass 4, I want to add numbers from 1 to 4, means 1 plus 2 plus 3 plus 4, definitely including 4. Because the range is going to be inclusive on the left side, which is not here, so it's going to be 0, and exclusive on the right side, which not include upper if I just use upper, which is 4. I need to say upper plus 1. So it's going to be 0, 1, 2, 3, 4, but not 5. Means upper 4 plus 1, which makes it 5. So for every single value in the range from 0, I'm going to say total, which initially I said it is equal to 0. So it's going to be 0 plus 0, 0 again. For the next round, it's going to be 1. Let me just. So what actually happens is, for the first time, this is going to be 0, but inside the loop, it's going to be first. The new total is going to be equal, whatever the total was, which was 0, plus the range that we have, which is going to be 0. So these two are going to get added and makes a new total, which is 0. The next round, I'm going to just show it like this. It's going to be 0 plus the new number in the range, which is 1, and just add it into a total. So it's going to make a new total equal to 1. Next time it's going to be 1 plus next number, which is going to be 2, and make it 3. And next round is going to be 0 plus 3 plus the new number, which is gonna be 3, because we already used 2, and it makes it new total, which is 6. And next round is gonna be 6 plus 4, which is a new number in the range, guys. The range contained 0, 1, 2, 3, and now 4, right? And it's going to make total equal to 10. By saying that, now if we run this for add number 4, we can understand why it returns 10, but it's a kind of iterative. What if I want to write the same thing, using recursive. So I'm gonna say for upper equal to 0, just return 0 for upper. Else, say upper plus add numbers upper minus 1. And what actually happens here is I'm gonna just use the same range of numbers. Sorry, I'm gonna use different color to make it easier. Imagine that we call add numbers 4. What actually happens is in the first round, definitely it's not gonna be 0. So we get to the else part and it's going to say return upper, which is gonna be 4 plus, let me just quickly say add numbers 4 minus 1, which is going to be 3. This one is going to call the function again. So add number, is the number equal to 0? No. Then it's going to be 3 plus add number 3 minus 1, which is going to make it 2. The same applies to here. So this time it's going to be 2 plus add number 1. And for 1, it's going to be 1 plus add number 0. Now we get to the base condition. And that base case is going to say it is going to return 0. So it's going to bring it back. And this is going to bring that back here. So the result of this would be 2 plus 1 plus 0. And the result of this is going to get back to here. So it's going to be 3 plus 2 plus 1 plus 0. And the result of all this is going to get back here, which is going to make it 4 plus 3 plus 2 plus 1 plus 0. You saw in the video that it's not the best approach in terms of memory allocation and speed, and in many of the factors, this is not the best practice. So if you have a solution better than recursion, please go that route. Sometimes that's the easiest in terms of understanding or applying. In some cases, like Hanoi Tower, if you haven't heard about it, just please, not a bad idea to watch a few videos about Hanoi Tower. One of them is quite a lengthy one, but that's amazing. So it tells everything in details. So for such problems, the best approach is recursive. Otherwise, it's not an efficient approach in general. Getting to the next example, so it talks about the factorial algorithm, and you know the meaning of it. Definitely in the video we watched it, and it shows the same thing. So now it says that if n is equal to 0 for factorial, we say it is going to return 1. So by convention, 0 factorial is 1. But for anything except 0, means any other positive integers, we are going to say it is n times n minus 1. So technically, here we have a base case or base condition in this part. In the case that n minus 1 is equal to 0, we know what to return, right? So this is the recursive form of factorial, saying if number is equal to 0, return 1, else return num times factorial num minus 1. So I quickly go through this with you guys for a small number like 4. So technically, you see that here, if we say, imagine that factorial, let's just show it by fact f. For what's gonna happen? Is 4 equal to 0? No, then it's going to get to this part, which is going to be 4 times factorial 4 minus 1, which is 3. We just consider this one again as like that. Because 3 is not equal to 0, so it's going to be 3 times factorial 2. The same thing for here, because 2 is not equal to 0, we're going to say it is 2 times factorial 1. And the same applies to this one, 1 times factorial 0. And now we have the base condition. So in that case, simply the result of this one, because factorial 0 is going to return 1 by convention, this one is going to make the whole 1. Then it brings it here. The result of that one is going to be 2 times 1, which is 2. Then it gets to this line. The result of this is going to be 3 times 2. And it brings 6 here. And the result of this is going to be 4 times 6, which is going to make it 24. If it is clear, please type 5. The good news is we are not very far from the end of today's session. So you see what is happening. We call different stack values. So this factorial is very much time consuming, but how about the iterative form of factorial? In that case, very simple. You're gonna, let me just use the same thing for this part and see how it works. So in that case, we pass, for example, factorial, let's call it just factorial 4f4. We are going to say fact is equal to what? 1. And then we say as number of is in the range of 1 to num plus 1 because it's exclusive on the right side. So we need to say from 1 to 5 to say, if we say from 1 to 5, the numbers that we are going to consider would be 1, 2, 3, 4, but not 5. So this would be the number that we are going to get into this number. Right? So we are going to say, what is the initial value for fact? 1. So we are going to say fact is equal to number times old fact, which was 1. So what is the first value in n? It's going to be 1. So 1 times 1 is going to be what? 1. So a new fact in the first round would be 1, right? Now, the next round, I'm going to say, again, this time we are talking about 2. 2 times what is the old fact? It was 1, and then we are going to bring this one into 2. Let me just go for the next round. So right now we have fact equal to 2. And then we are talking about the next element in the number, which is 3. So the result of this for the next round is going to make it 6. And so we are going to have a new fact. 6, guys, when I say new fact, I'm talking about this part, right? 6. And now the last number would be this one. So I'm going to say this time 4 times 6, and it's going to make it 24. The thing is, in terms of memory, I have provided something for you to show you guys in the recursive form. Imagine for every single of these function call, if we just occupy 10 bytes, it's like 10 multiplied 4 for the sake of this simple tiny teeny recursive function means 4 times 10 bytes. While if it was this mechanism, you see, we just override the values and we do not have any stack and calling function again. So it's a very memory efficient way and very fast. Normally, the loops are optimized in implementation and they are faster in compared to stacking calling functions on top of each other. So the do it yourself part, I have borrowed some examples. For instance, here, if you see recursive factorial from different tutorials with their explanations, and I thought not a bad idea to go through these examples. The other one is using product of two numbers using recursion. This one is using kind of sum plus using multiplication for the multiplying two numbers. And this is a small version without comments. And I'm going to quickly go through something similar to this and explain that. Imagine that I'm going to call a product, let's say product, and I'm gonna say, what do we call it? For instance, 5, 2. This one works pretty fine. We are gonna get to that. Let me just start with an exception. Product. I'm sorry. Saying 2, 5. In that case, in this line, it says, hey, if x, in this case it is 2, is less than 5, then just return the swap version of that. Means let's call product and say 5, 2. The intention is to have the left number greater than the right number. The only thing later you're gonna think about what I'm telling you at the moment. It's just to use the memory, use the steps to keep the steps simpler. Now that we have product 5 and 2, let's see what's going to happen. As long as y, or this part, is not equal to 0, just say 5 plus, let's just say prod 5, y minus 1, which is going to be 1 here. Again, we have this part. And for this one, because this one is not equal to 0, let's say it is equal to 5 plus prod what? 5, 0. Now we get to the base condition. And that base condition is nothing but saying because it is equal to 0, so just return 0 for that. So for this one, we are going to return 0. So it's going to be 5 plus 0. And the return of this step, which is 5, is going to get added to the previous one. So this one is going to be 5 plus 5. and the result would be 10. By saying that, now we can completely understand why here, if I say 5 and 2, it's gonna give me 10, which is 5 times 2. The same applies to 2 and 3, so it's gonna be 3 times 2, and it's going to give us 6. One of the series that an Italian mathematician announced it to the world of science is Fibonacci series. And it is something like 0, 1, 1, 2. And look at this one. 0 plus 1. Let me just show you this value. Here, here 0 plus 1 creates this number, and 1 plus 1 create this number, and 1 plus 2 create the next number, and then 2 and 3, and you go all the way to the right like that. So if at the n, guys, n is, I'm sorry. As you see, n here is equal to 0, and n is equal to 1 here. So it says if n is equal to 0, return 0. And if n is equal to 1, return 1. Else, that's what we actually do. We say return n minus 1 plus n minus 2. Imagine that you want to calculate 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So n equal to 9. So one way is saying that simply for n equal to 9, return Fibonacci 8, which is 9 minus 1, plus Fibonacci 9 minus 2, which is going to be 7. Look at the thing that I have provided before. For instance, for 5, you say 5 minus 1 and 5 minus 2. And for 4, you say 4 minus 1 and 4 minus 2. And for 3, do the same thing till the condition that you get to the leaves or the base cases, right? Like Fibonacci 0 returns 0, Fibonacci 1 returns 1. So we are going to have those values and we get them together. This is how it works. So by saying that, and look at this one. So 1 and 1, 2, 2 and 3 creates 5, 5 and 3, 8, 8 and 5, 15, and so on and so forth. And the beauty of Fibonacci is you can see it in many facts in the nature and in the universe. And I heard that you can just read more about this, that our eyes and our brain finds beauty in the pictures that has Fibonacci into it. So look at this one, guys. This definition is a recursive definition of Fibonacci. We say if n is equal to 0, return 0, and if n is equal to 1, return 1. Else, go back to that, like n minus 1 plus n minus 2. And the good thing is, we are going to go back, for instance, in the example that I told you. So we start from 8 and 7, right? And then this guy is going to get to Fibonacci of 7 and 6, and this one is going to get to the Fibonacci of 6 and 5, and we go all these branches till the time that we get to 0 and 1, and we can simply return that. So it's not a bad idea that you spend a few minutes going through these series by yourself. I say that for I in range, if you just simply say what is the Fibonacci of 10, simply it's going to remember I in front of your eyes, I just said let's just consider 9. And this is going to be number 10, right? So the Fibonacci of 10, f of 10 would be 55. Look at the result here. So if I say Fibonacci of 10 using that, let me just run, it's going to tell you 5. How about if I say 9, for example, it should show you 34. But what if you want to show all the Fibonacci series? So simply I said from I in the range of 10, right? So when you say 10, it's going to be from 0 to 9, but not 10. So it's going to show you 0, 1, all the way to 34. But what if I want to have 10 as well? So I'm going to add 1 into it, and it's going to show you like. You might say, Reza, is it possible that I get rid of that comma at the end? Yeah, you can simply say if I is equal to 10, then the end should be just nothing. But for the rest, you print the value, Fibonacci of 0, Fibonacci of 1, 2, 3, 4, 5, 6, 7, 8, 9. You're going to just terminate the print by comma. But for 10, for I equal to 10, you're just going to say, hey, don't use that comma at the end. This is what I showed you a few seconds ago. But this is iterative form of Fibonacci and not recursive. You can guess that if n is equal to 0, just return 0. If n is equal to 1, just return 1. But what if you just enter any number greater than 0 or 1? In that case, what we actually do would be simply we say, okay, we know the numbers, like for, let me do one more thing here to help us a bit better. And that is having this Fibonacci series. What we actually do would be saying, hey, if I is not n1 and n2, so it is definitely something in the range of 2, means here, all the way to whatever we want to have, like, let's say 9. So we are going to say from 2 to 9 plus 1, which is 10. What we do is look at this part. Okay, what is n1? Right, n1 is 0. What is n2? n2 is 1, right? So technically here we say fib, a new value, fib is equal to n1, which is 0, plus n2, which is 1, based on these two, right? So now we have fib, and we want to, guys, imagine that we slide these two towards right. How we are going to do that? We say a new n1 was here, but a new n1 would be what it was n2 before, You remember it was N1 and N2 in the previous attempt. So N1 is going to be the old N2, which technically is nothing but 1 in this step. And N2 is nothing but the summation of the previous N1 and N2 based on this, right? So this is going to be a new N2, which was fib. So we are gonna place fib into that. So it's gonna be 1 there. And for the next round, you can see again, we are gonna see fib is going to be N1, which is 1, plus N2, which is 1. And after that, we say a new, let me just show you this one. A new N1 is what it was N2 in the previous attempt. You see that? And a new N2 is nothing but we had as the Fibonacci fib 1 plus 1, which was 2. And we go like that, right? So by saying that, in this iterative format, you can see the same thing. If you just say 10, it's going to go from 0 all the way to 9, not 10. And the thing is, I created here, like, I just modified it a little bit to make it nicer, neater. Not to need to use 4, but if you say 10, for example, it's gonna go from the beginning all the way to the end. So let me just run that. So it's going to print N1, which is 0, and N2, which is 1, and then it goes from here all the way, adding those two numbers. And if it is not the last number, just use comma to separate them. And if it is the last number, just don't use comma. This is something that I just added to the board. I strongly recommend that if you want to grab more content, check Hanoi Tower in recursion. And by saying this, we are done with the content of today. I'm gonna close the video, but those who are in the class, please stay for a few seconds. I just want to make sure that the quiz works. Those who watch the video, thank you very much. Have a wonderful one.